Yeah, let's start. So they to keep our schedule on time. So this is the second day of our section for the software upgrade, this control system upgrade. And our first speaker is Luigi Machis from ETH at Zurich. So Dr. Machis got his PhD in particle physics from Oxford University in 2019, and he currently a postdoc researcher in the particle physics working in the CMS Corporation at CERN. So he is currently a coordinator in the detector control system and the safety system for the ICALEPCS detector. He will talk about the upgrade of the CMS ICALEPCS detector control system during the CERN LHC non-shutdown too. So please.
Okay, can you hear me and see me? You should be able to hear me and see me.
Yes,
okay.
We can hear you, we can see you.
Okay, I'm going to share my slides then. So you should be able to see that.
That's right, yes, we can.
Okay, so good afternoon. So I'm Luigi Marchese, and so I will be talking of the upgrade of the CMS electromagnetic calorimeter detector control system during the CERN Large Hadron Collider launch down number 2. So the CMS experiment is one of the 4 proton-proton interaction points of the LHC ring. It's a multi-purpose detector with a broad physics program. After successful data-taking years, we just recently concluded the run-to data-taking period. The machine is now currently in the second long shutdown for the LHC, which is meant for machine maintenance and upgrade of the LHC detectors. Due to this COVID-19 pandemic, this LS2 has been extended by 1 year and will finish by March next year. So the CMS electromagnetic calorimeter is an hermetic fine-grained homogeneous calorimeter with more than 75K lead tungsten scintillating crystals. In this slide, you can see a photo of the detector where you can see also the partitions we consider, because it's conventionally split in different partitions depending on the directions of the coverage we are looking at. So there is the end cap section in the forward region, the barrel in the central region, and in addition there is also a lead silicon-based pre-shower in the forward region. The detector was designed to operate for at least 10 years. It has been so far successfully supported run 1 and run 2 operation indeed for more than 10 years. So the CMS ICAL detector control system was needed since the challenging design constraints, and I will convince you of these in one slide, in 1-2 slides, of the ICAL required a sophisticated detector control system with some main functionalities like autonomous control of ICAL to ensure data-taking operations, monitoring of ICAL working conditions when taking data, and communication with several services. The system is a distributed and redundant system where hardware communication is based on industry standards as OPC, Modbus, and S7 protocols. The ICAL DCS software is based on a 3-Dell Blade server, Windows-based, plus a replica, which is available in case of failure. As I said, it's a distributed and redundant system, so we have always a replica in case of failure. Here in this slide, you can see the main ingredients. So we start from a layer of the commercial WinCC open architecture produced by Siemens. On the top of it, there is a CERN dedicated software, the CERN JCOP framework, and I will be adding more details on this later. Then on the top of this, for the specific experiment, we have some components developed, some software developed by the central detector control system team in CMS. And on top of this, there is also the CERN finite state machine for a more abstract level of the detector. So in this slide, you can see the simplification of the detector thanks to this CERN software, the finite state machine. Thanks to this logical grouping into a hierarchical tree-like structure, we can actually see how basically there is this interconnection between what is seen by the CMS detector control system shifter in the CMS control room and how this connects with the real detector. So we have these node tree-like structure where you start from the first node, which is the central detector control system, and then you move forward to reach the other sub-detectors DCS, so tracker, ICAL, and we are now focusing on this specific one, the one for ICAL. When moving forward, we reach the partitions subdivision, I mentioned it before, and you could appreciate in the previous slide geometrically, and then you reach low voltage, high voltage, and final connection with the hardware. There is, of course, a user-friendly interface thanks to this FSM, which is really important because allows non-expert shifters to operate the detector on request. You can see it, how this is seen simply in the CMS control room. This is the geometrical representation of the ICAL detector with the subpartition we described before. Behind this simplification, there is enriched DCS complexity with more than 1,300 sensors for temperature, humidity monitoring, almost 2,500 channels for low voltage, high voltage, more than 100K monitoring parameters, and a total of 27 software components. So it's really important to have this DCS because the design, as I said, required some monitoring of temperature stability in the environment of the ICAL crystals and of the photodetectors. Several thermistors were implemented in the structure with a precision better than 0.01 Celsius, and also some humidity measurements, precision humidity measurements were needed to monitor air humidity inside these ICAL compartments. With this sensor able to reach 5–7% of relative precision. In this slide on the right side, you can also appreciate how they are located within one of the super modules, 4 modules of the ICAL detector, where you can see arrows indicating some of them, how they are located inside. So the ICAL DCS services, the ICAL DCS is organized according to several services it provides, interacts with. So we have the starting point, the platform, when we have connection with these external power services, where we have low voltage for the ICAL, for the pre-shower, and high voltage as well. Then there is the proper monitoring services, which is embedded as part of the ICAL DCS, precision temperature monitoring and humidity monitoring, which I hope I convinced you of the needs in the previous slide, and then some other external services like the CMS, magnet control system, the cooling system, or safety services for the ICAL and the pre-shower detector. So during the current LS2, the ICAL DCS went through some software migrations, which can be grouped into 3 main blocks: WinCC/OA in JCOP control framework migration, a version control system migration, and OPC UA. The first one, we now go in more granularity for each one of them. The first one, the WinCC/OA, was the platform was migrated from version 3.15 to version 3.16. This was part of a CMS-wide plan to migrate all the sub-detector DCS to the up-to-date releases by Siemens. So the major point is that WinCC/OA 3.15 was based on the ISO encoding for Latin, while the new version is based on the UTF-8 encoding. And there were also some new XML file format for panels in WinCC/OA 3.16. This required us to basically develop an automatic tools to check in the ICAL DCS source files for all encoding incompatibility, to apply some automatic corrections and to convert also the panel format from the previous version to the new one. And this has been successfully done. So still part of this group, there is then the migration of the JCOP framework. The Joint Control Project, JCOP, is a CERN collaboration aiming for a shared control system architecture to be used LHC-wide. Since this is a software developed on the top of the commercial WinCCOA, every time that there is a new release of WinCCOA, of course, you must have a new release for the JCOP framework released, of course, by the CERN appropriate group. And on the contrary of the JCOP framework version 8.2.1.2, which was compatible with the previous WinCCOA version, the new version 8.4.0 requires some change, because now functions require an explicit call for required libraries whenever there is a need. So this required us to check for, again, ICALEPCS source codes with an automatic tool called Code Purger to check for resolved calls and to implement automatic change. And this has also been successfully done within this migration. Now we move to the second block, version control system. In 2018, CERN abandoned the Apache subversion system SVN for the Git distributed version system, and this required us to migrate from the previous SVN repository to the new Git repositories. We also took the chance to reorganize a bit the Git repositories, moving from a single monolithic SVN repository to a set of 35 different Git repositories organized depending on their functionality.
So you have 4 minutes.
Yes, sorry?
You have 2 more minutes.
Okay, sure. So then there is the OPCDA to OPC-UA migration. OPCDA is the industrial standard largely used for hardware communication at CERN since the 90s. Following the release of the new standard OPC-UA, CERN decided to migrate all the OPCDA servers, and this has happened in CMS along with the migration I described before, with some improvements regarding platform independence and improvements in security and modeling. Here we can see with a zoom one of the communications between the WinCCOA driver, the OPC client, and the corresponding server. In the ICALEPCS, 3 different servers are used. So we have Wiener for low voltage for EE and DB, Kind for EE and DB for high voltage and for the pre-shower. And then there is the CERN-made module embedded local monitoring boards for precision temperature monitoring. So this migration required a reconfiguration of the address space for the various components that are in use, and this has been also successfully done in the ICALEPCS project. An additional software modification was also needed following this migration I described, because the component dependency change to be followed when installing a new component was affected by the migration. So we migrated the ICALEPCS installation toolkit accordingly. In parallel, and to conclude this migration section, so we also took the chance to improve the notification system, which in past was organized by a group of users, so allowing basically users to receive multiple alerts when needed. And the new one is now based on the new CERN e-group system, and so by application domains, preventing from multiple messages to be sent to the same user. So in conclusion, after several successful years during run-2 operations, the CMS ICALEPCS project went through major modification during the LHC second long shutdown. And multiple migration took place progressively, with the final migration happening in July 2021, together with the rest of the CMS detector control system, moving from the WinCCOA platform to the JCOP framework, then SVN version control system to Git, OPCDA to OPC-UA. In parallel, we also improved the notification system. The ICALEPCS team was one of the first teams to migrate the project within the deadline, which was the start of Run-T, March 2022, so well advanced of time, with a small group of 6 people and only 2 more involved. And this is one of the most aggressive and complex migrations since the start of the CMS project. The system is now ready for Run-3 data taking operations, which will start next March. With this, I'm done. Thank you.
Thank you, Luigi. We are quite close on time, but if there's one short question you can handle.
Sorry, I messed a bit with time.
It's okay. We started a couple of minutes late, so it always happens at the beginning. Any questions from anybody? I think you mentioned how big your teams were. Did you say a 6+2? And
Yeah,
over what period?
Total 6, the ones that are reported as the authors of this paper, but 2 of us were the ones more actively involved on this migration, which was a massive one. You know, we needed to be sure that everything was ready before the start of run 3, which is approaching soon.
And how long before now did you start? How many years have you been in preparation?
For this specific project, we started preparing everything in about 1 year ago. So let's say summer 2020.
Oh, nice. Okay, thank you. Okay, we should move on there. Back over to you.
Okay.
Thank you very much.
Okay, the next speaker will be Tigran from KIP in Hamburg. Tigran is a graduate student at the KIP in Hamburg University. So, please.
Hello, yes. Can you see me and hear me, I hope?
Yes.
And I shall share the slides, and I think you can see them. Okay, should I start?
Yes, please.
Okay, thank you. So hello everyone and welcome. I will be presenting you also an LHC Atlas. In an LHC talk, it will be about the upgrade of our current level 1 calorimeter trigger system and what we're doing for the next set of runs from the LHC. So let's dive in with the Atlas trigger and data acquisition system as an overview. As we have proton-proton collisions at around 40 megahertz, we require a multi-level trigger system in order to filter out all the interesting events and write them to disk only a certain amount as we have bandwidth limitations. And for that, we use a level 1 trigger, which is fully custom hardware. You can see it here on this side. Which has an acceptance rate from going down from 40 megahertz to about 100 kilohertz of filtering. And then once the decision is based on, it is sent to our high-level trigger where a processor farm is running various algorithms, and these reduce the acceptance rate further to about 1.5 kilohertz. And the level 1 trigger decision that has to be performed has a latency of a maximum of 2.5 microseconds. So we have to use, we have to be quick in our decision making. This talk will focus mainly on the calorimeter trigger that is here in black. And let's go dive deeper into the electronics of this trigger. So here you can see an overview of the L1 Calo system as a whole. It is a hardware-based pipeline system. And it processes both of the Atlas calorimeter signals that are sent through. So in blue, you can see the current system that has been running since the start of the LHC. While now in yellow, we are adding the new so-called feature extractors, which will perform quite more sophisticated algorithms than before. So the main tasks for L1 Calo is to identify electron, gamma, and tau candidates, small and large radius jets, and also to calculate the missing transverse momentum as well. And the sum of the momentum. So while the upgrade here you can see brings quite new electronics, which we'll talk about in the next slide. And one thing I would like to mention is that we will, once the LHC starts again, we will run with the old system that we have with the legacy system in parallel with our new upgrade in order to perform a full validation of it. So you might ask why we want to upgrade. As we keep increasing the luminosity at the LHC, we have a much higher challenging pileup environment, and hence we need more bandwidth and more better performing electronics in order to cope with that. And also we would like to upgrade our system in order to perform much more capable algorithms than they were possible before. One of the highlights of the upgrade is also that we will get quite a higher granularity cell information from our liquid argon calorimeter. So previously, before in the previous LHC runs, we had these so-called trigger towers, which were quite granular than the actual liquid argon detector itself, with having a delta eta, delta phi of 0.1. With this new upgrade, we will get a much granular system, as you can see here, where once you could see only one electron in a single tower, we can see the full shower shape. And the new electronics will take complete advantage of this higher granularity in our trigger system. And this will, of course, act to reduce the level 1 rates while maintaining low thresholds. Here I would like to show you a brief overview of our hardware upgrades. So you can see the main feature extractor modules here. These are all ATCA based, and they all perform various different algorithms. So for example, the electron feature extractor is here for identifying the electron, gamma, and tau candidates, while the jet feature and the global feature extractors perform jet algorithms and also calculate the transverse momentum. We also have a slew of further modules which are included here. For example, the level 1 topological trigger, which also performs different multiplicity counting and further algorithms downstream. And we have the tile rear extension module, which provides the hadronic inputs to the new feature extractors. We have this so-called hub and rod readout driver, which is used in order to read out from a single ATCA shelf all of the modules and transmit them to our readout system in Atlas. And then we also have, in order to connect all these modules together via high-speed optical fibers, we have called fiber optic exchange boxes, which include over 7,000 fibers and do perform all the mapping between the modules here. So we have some studies done to see what kind of performance we expect, and we can see a significant improvement in the energy resolution. For example, you can see it in the upper right plot, and also much more improved efficiencies and sharper turn-on curves seen here in the bottom plot. Here I show you one of the effects performances. This is based on simulation, comparing previous run 2 data with the expected performance of the new hardware. The same is shown for the JFEX and the GFEX processors as well. Here you can see the simulation performed and compared with the offline, so-called offline algorithms, and also the previously used trigger algorithms, and we can see that the efficiencies improve quite a bit. Going now to the installation, so I would like to show you how we're doing, and this is currently an ongoing project, so we're installing and preparing everything for next year when the collisions will start happening. So it's a very alive and dynamic system that is currently seeing changes on a daily basis. So what we have is 3 racks full of ATCA shelves. So here you can see how many that we have. We use 4 PCs for our detector control system in order to monitor all of the new hardware that is being installed. We also have multiple monitoring PCs and for control and connectivity. And of course, we have now for the commissioning period also PCs for debugging and JTAG. All of this together, we have also intra-connected fibers, which are mostly around 6,000 fibers, which go from the modules to the various other downstream systems. And all of the modules undergo validation at CERN both and the home institutes before going to the main detector. So in our installation status, I just would like to show you what we've done now from all of our modules. So the GFX system and the TRX systems have all been installed completely from the effects. System 6 are installed and 18 to be installed in early 22. The JFX module is half of it has been installed, and we also aim by the end of the year to install the further modules that remain. Our topological processor, one of the processors should be installed by the end of the year, and the rest of the infrastructure, such as the hub and rod and the Fox, have been installed or are about to be installed as well. So yes, commissioning. So we are commissioning the hardware in our surface test facility at CERN. So this is a test rig. Here you can see one of the pictures for single module tests, where we have at least one module from each flavor, where we connect a full vertical slice and it undergoes testing with all of the infrastructure and software that is needed in order to perform, to emulate a setup within Atlas. And here we have been very successful with achieving a full combined readout from all of our modules. And we've tested also the high-speed link transmissions between the modules here as well. And this has been going on further. And what I would like to mention is we will keep this facility ongoing in parallel with the activities ongoing in the main Atlas detector in order to validate and continue improving our firmware here at CERN. Just a couple of highlights of the actual installation of the modules. So in Atlas point 1, as you saw from the modules that are installed, we've been successfully testing and integrating the modules in point 1. And in Atlas, and we've also performed various different tests in order to validate all of the interconnectivity. And as of now, speaking today, we have our first LHC pilot beams where we will fully exercise the system and see the performance of the installed modules. So yes, that was my last slide. So this brings me to my summary. We have a huge effort from experts from many places of the world. We have in total 15 institutes working on this project. During the COVID times, we had experts working. We had a core group of people at CERN and many experts contributing remotely in order to perform all of the installation and testing. And we've been efficient, but of course it would have been much better to be there in person and do all of this. But this is now ramping up. And now we can have more people on site, and we're in great shape in terms of firmware and software, and the modules are also ready and being installed. So we have achieved quite a lot of things in the last year, and we're ready for some pilot beams from the LHC. And here I show you some pictures from the effort. That's all from my side. Thank you.
Okay, thank you, Stephen. Do we have any questions from anybody? I can't see any coming through. So you commented on how many groups of people have been working with you on this, and how long ago did you start the initial planning of this upgrade?
So the very initial planning was actually the technical design report was written in 2013. However, there were quite a bit of changes in throughout, and the project really ramped up in the last, I would say, 3 years. So as the firmware development got ramped up, and the modules, the prototypes and the pre-productions started being produced, it was about 3 years ago.
Okay, thank you. Right, I think we should move on then to our next speaker.
Also, there is one more question in the who they say, how did you manage the cooling aspect of the FPGA boards?
Yes, I replied to that a bit, but as you can see here, for example, you can see all of the, these are all ATCA standardized modules with quite large heat sinks on the FPGAs, and we are running in an environment with water-cooled racks in Atlas, and we still have a sustained temperature of about 20 degrees of the water temperature, as you can see here, these blue racks here, and we have the ATCA shelves set to quite a high rotation per minute on the fans, and so far the temperature has been quite good in terms of operation.
Okay, that's great. Maybe we should move on to the next. So the next speaker will be the Alexei Trifonov from the Joint Institute of the Nuclear Research in Russia from Moscow. He will talk about the control system of the Linux 200 electron accelerator at the GINR. Yeah, Alexei, please.
Okay, thank you very much for introduction. Can you see my slides?
Yes.
Okay, thank you. I would like to start my talk then. So, hello everyone, my name is Alexei Trifonov, and I will talk about the control system of the Linux 200 electron accelerator at the Joint Institute for Nuclear Research. So, the control object is a linear electron accelerator. At the moment, it has 4 accelerating stations, and the electron energy is about 200 MeV. In the future, it's planned to increase the number of stations up to 13 and increase the energy up to 800 MeV. For now, the electron beam is available for users in 2 places, after accelerating station number 1 and after accelerating station number 4. The main parameters of the electron beam are presented in the table. So this facility is intended for scientific and methodological research in the fields of accelerator physics and technology, elementary particle detectors research and development, as well as fundamental and applied research in the fields of radiobiology and material science. And Linux 200 electron accelerator is based on the medium energy accelerator, which was transferred to GNR from Dutch National Institute for Subatomic Physics in the ends of 90s. So almost all accelerator equipment was in the good conditions and has reasonable operation resources. However, control system hardware and software, as it's like most rapidly developing sphere, were mostly out of date already at the moment of accelerator was transferred. In the mid of 2000, the first upgrade of the control system was carried out. I will not go into details about this upgrade. I just will say that a number of standalone systems were developed, which made it possible to carry out a staged launch of the accelerator. And however, we need a second upgrade of control system because for accelerator operation as a facility for users, the global control system is required. This system, like this new control system, should be highly reliable and serviceable. Also, it should use standard interfaces for communication between components and have a possibility for future modifications and extensions, and also have a possibility of using existing developments of the world community. So the new control system will be based on Tanga controls. Tanga is a free open source device orientated toolkit for controlling any kinds of hardware or software and building SCADA systems. Tanga was chosen because it's flexible and highly scalable, and because our colleges from Wexler and Baldwin Laboratory of High Energy Physics in GNR use it for implementing the Nika Collider control system. So Tanga software could be split on the device servers and client applications. Device servers communicate directly with hardware or with different software systems via some specific protocols. And client applications provide a graphical user interface for interacting with device servers. And Tanga incorporate a number of tools to build efficient control system environment, including centralized administration and monitoring, access control, logging system, data archiving, and code generation for rapid development of Tanga device servers using such languages as C++, Java, and Python. So here I would like to talk about concept of the new control system. Conditionally, the system could be divided into 3 levels: the hardware access level, server level, and the client level. At the hardware access level, digital and analog signals are collected and analog signals are converted to digital. And this level also includes all equipment that needed to be controlled. The hardware access level is connected to the server level through the data transmission channels. The server level is required for efficient centralized collection, processing, and storage of data from the elements of the hardware access level, as well as for implementation of subsystem control algorithms. The client level provides graphical user interfaces for monitoring and controlling various parameters of the accelerator. Also, it's a possibility to transfer the necessary data to the electron beam users. So the Linux 200 global control system is based on the interaction of components, including in the Ethernet network, divided into a number of segments, which are serving to the main control room, accelerating station in each accelerating station, and user control room and the accelerator hall itself. So local control is available for modulator control units and phase shifters. It's done with touch panel by Vintech companies. In addition to display the local control graphical user interface, panel acts as Modbus servers. So slave devices are connected to the panel by means of RS485 interface according to the Modbus R2 protocol. Data is transmitted to the Tanga-based global control system via Ethernet using Modbus TCP and Modbus R2 over TCP protocols. The other subsystems have the ability to control locally directly from the equipment. We use Linux as an operating system, and we use stable version of Tanga, which is available in the Debian and Ubuntu repositories. Tanga server is written in C++ and Python using PyTanga. Also, we use Qt5 and Qtanga library for building client applications with graphical user interfaces. In the future, it's possible to use the web clients, and also the possibility of using TUARs or Cumbia libraries seems pretty promising to us. So Linux 200 control system has several subsystems, such as the electron gun system, which is described in details in the Mikhail Nazdarin report, and that was in this conference. The new synchronization system, for which the currently used standalone software running under the Windows PC, but in the future it's planned to develop a Tanga-based software for this purpose. So at the moment, RF control subsystem includes master oscillator, preamplifier, and cluster modulator control units, as well as phase shifters for V2 control. So our vacuum system is controlled by programmable logic controller from BNDAR Industrial Automation. Software for this controller was developed in C language, and interaction with the global control system is carried out through the Modbus TCP protocol. And so for accelerator structures, precise temperature regulation, we plan to use the unicellular circulators from the Huber company. And I wouldn't talk in detail about this, just will say that a special Pilot 1 unit would be used to control the circulators. And I want to talk about focusing and steering magnets control in a little bit more detail. So magnetic elements are used to focus and steer the position of the beam, which are mainly required to reduce the loss of particles during acceleration. Focusing is carried out using the solenoidal and quadruple lenses. Steering magnets are used to adjust the position of the beam related to the accelerators. For powering magnetic lenses and steering magnets are used power supplies from Corad company. Corad power supplies have interfaces for remote control, which is unsuitable to transmit the data over the long distances. And also these power supplies doesn't support standard communication protocols. Therefore, to control Corad power supplies, we designed and manufactured specific intelligent interface modules. And the magnetic elements control system scheme are presented on this slide. So data exchange between this system and the global control system is implemented using Modbus R2 over TCP protocol. Since the existing Tango class does not support this protocol, a new class to handle the Modbus protocol was implemented based on PyModbus library. And on this slide, you can see the Tango client application for controlling magnetic system. So I would like to go to my conclusion. And in conclusion, I would like to say that at the moment, the general concept of the global Tango-based control system has been designed. And right now, our accelerator building is undergoing major repairs. And of course, due to COVID pandemic, it was really long, but we hope that it will be ended pretty much soon, but by the end of this year. And it's planned to integrate Tango-based software when the accelerator is launched after the first phase of repair. So, and I would like to say that we are grateful to the Nika Collider control system team for useful discussion about control system architecture and Tango-based software development advices. And we are grateful to all Linux 200 engineers who participate in discussions and provide us with useful comments and ideas. And lastly, I would like to say thank you to the organizer community of this conference to organize such a beautiful event and having me here. So that's all from me. Thanks for your attention.
Thanks, Alexei. We can move on to some questions. There's one posted already. Why did you choose C++, Qtango, and Java for the Tango clients, considering that many facilities are moving towards Python and the web?
Okay, so we actually don't use Java. Maybe I say something incorrectly, or maybe somebody understand me incorrectly, but about the C++ and Qtango, we use this library mainly because I have experience with creating applications in the Qt5 framework. And we have like really small team of people that can develop applications. So I just start develop it with Qtango library. But as I said before, really promising ideas is using Taurus and also using web clients like it's mentioned in the questions.
Okay, thank you. And the second question, do you see the future use of web client applications as a strategic and gradual move away from Qt, or do you see it more as just an additional type of application?
At the moment, we think that in the near future, we probably will use it as additional types of application. But if it will show great qualities, then we probably will switch completely from the Qt applications to the web applications based, for example, like web frameworks like Vue.js, AngularJS, or React.js, and something like this.
Okay, thank you very much. There are no further questions, so thank you very much, Alexei.
So I will stop sharing my screen now.
Yes, if you stop sharing, yeah.
Yeah, so is there any other questions from attendees?
Or we can hand over to the next session, can't we?
Right. Okay, thanks.
Thanks, everybody. That was good. Hand over to the next session.